I can accelerate time and calculate the position of the center of the universe. Here's the issue. I don't have an answer yet, and I believe no one does. However, AI might be able to propose a hypothesis consistent with my expectations. It is often said that as we approach the speed of light, time approaches zero. This is relative, of course. Acceleration is acceleration. This may sound redundant, but it isn't. Suppose an object moves in the opposite direction of Earth's rotation around the Sun. This initial movement can be viewed as reverse acceleration. This definitely slows time. But what if we view it as staying stationary, no longer rotating with the Earth around the Sun? If it flies outward to counteract the Sun's gravity or releases a nearly massless substance, would its time pass faster? Would this be equivalent to deceleration rather than acceleration? Now consider this from the perspective of the Milky Way's center. If the solar system orbits the Milky Way, but this object resists following the solar system, instead maintaining its position using propulsion, what happens? You might argue that this is still acceleration rather than deceleration. Flying backward or forward are both acceleration relative to Earth. That's fine. We could launch probes in at least 4 directions, or even 16 directions to measure their time progression. If time slows equally in all directions as they approach the speed of light, this experiment fails. But what if, after leaving Earth and maintaining a stationary position relative to the Milky Way's center, time slows even more? Alternatively, a spacecraft accelerating cannot escape the problem, so we could land on a star with an orbital speed around the Milky Way slower than the Sun, release an atomic clock, and measure time progression, while eliminating gravity's influence on time. This could reveal what position in the universe is truly stationary, thereby identifying a relative center of the universe. Even if it's not the true center, assuming the universe is a sphere, it still represents a relative middle point. If the universe is elliptical, for instance, with 2 centers, the midpoint between them can be considered the center. By doing so, the universe's center of mass can be inferred. Much like how humanity cannot directly measure time stopping at the speed of light, we can observe changes at 0.1% and 1% of the speed of light to deduce at what velocity mass becomes infinite and time stops. The concept of time reversal beyond light speed is merely mathematical speculation. Time doesn't necessarily reverse. It merely stops at light speed. Any faster-than-light conclusion about time reversal remains a hypothesis. By measuring time in various locations, we can deduce the universe's center and understand its direction of motion. If time speeds up while maintaining relative stillness, it will point to the most central spot in the universe where time passes fastest. Finally, the gravitational effect on time must be excluded, which is not hard to accomplish. Estimating the mass of observable galaxies could help isolate gravity's influence. With such exclusions, the ultimate goal can be pinpointed, answered by ChatGPT-4 Omni. 1. The relationship between time and motion. Theoretical basis. According to the theory of special relativity, time dilation depends on an object's relative velocity and the gravitational intensity of its position. The closer to the speed of light, the slower time flows. Strong gravitational fields also slow time. Feasibility analysis. The experiment proposes sending multiple probes to measure time changes in different directions. While theoretically feasible, practical challenges include precision. Extremely accurate atomic clocks are required to detect minute time differences. Energy needs. Probes must sustain long-term, stable motion to maintain relative stationary positions. Reference frame. Using the Milky Way as a reference frame needs validation for its universality. Second, relative stationarity and the center of the universe. Core issue: whether there exists an absolutely stationary reference point or center in the universe. Current theories suggest no absolute reference frame. Motion is always relative. Challenges: using a fixed frame like the Milky Way may not yield universal conclusions. Cosmology often assumes isotropy and homogeneity, no specific center, from a Big Bang perspective. Locating the mass center. Theoretical possibility: Using elimination and measuring time variations in various directions to infer the mass center is an indirect but potentially insightful approach. Difficulties. Data needs. Vast temporal and spatial measurements are required for comprehensive conclusions. Gravity isolation. Completely excluding gravitational influence on time is challenging, as gravitational fields permeate all space. Fourth, technical limitations. Demands highly precise measurement instruments. Long-distance exploration requires breaking through current space exploration limitations. Conclusion. The experimental methods proposed in the document have theoretical value but are challenging to implement with current technology. The idea of identifying the universe's center is more of a theoretical exploration since an absolute center might not exist. However, such research could contribute to a deeper understanding of the universe's fundamental properties.